Hello, hello, hello. In this worked example, we're going to talk about how to use the work kinetic energy theorem to calculate something that you'll actually also measure experimentally as a lab activity. So a pendulum is nothing more than some sort of uh, mass that is attached to a pivot point by either a rod or a string, and you displace the mass away from its equilibrium position, and you let it go. And the question is, as it swings, what's the fastest speed that it's going to be moving? And you can probably guess that it's going to be moving fastest when it goes through the equilibrium position. But how fast? Can we calculate how fast? Well, it turns out that this is a great example of where the work kinetic energy theorem makes answering this question very simple. So let's dig in. Okay, so the problem is we imagine taking a pendulum consisting of a mass that we can treat as a point mass of mass m on a string of length L, and we displace the pendulum by an angle theta away from the vertical position, and we let it go, and we'd like to calculate how fast the pendulum bob is moving when we get to the vertical position. And the claim is that the work kinetic energy theorem will make light work of the problem. And to remind you, what the work kinetic energy theorem says is that if we identify a system that consists of a point mass, and that's certainly going to be the case here because our system is going to be the pendulum bob, which is a point mass. And we let the system go through some change in which there is work done on it by external forces. And we want to calculate the net amount of work done by all the forces acting on the system. And the work kinetic energy theorem says that that should give us the change in the kinetic energy of the point mass. And of course, the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. The initial kinetic energy in this problem is zero, since we're releasing the pendulum bob from rest. And the final kinetic energy is just equal to 1/2 mv max squared. And by v max, I simply mean the speed, the maximum speed that the pendulum bob has when it reaches its final position. That is the position, the final position is the position as the pendulum bob is sweeping through its equilibrium position. So all we've got to do to find V max is to calculate the net work done by all the forces acting on the mass as it moves from its initial position to its final position. And to calculate the net work, we need to first identify the individual forces that act on the mass so we can calculate the work done by each of those forces. And in this problem, there's, of course, the gravitational force, which points in the downward direction. And then the string can exert a tension force located along the line of the string. So I'm going to draw that force this way, and we'll call it F sub t for a tension force. And as the pendulum swings, the tension force is always directed along the line of the string. So we can write from the work kinetic energy theorem, we were going to calculate the work done by these two forces. The net work is the work done by gravity plus the work done by the string. And that should be equal to 1/2 mv max squared. So in order to calculate Vmax squared, we're just going to need to calculate the work done by gravity and the work done by the string. So let's start off by calculating the work done by gravity. Well, by the definition, when you have a constant force, mg, the work done by that force is just the scalar product of mg with a displacement when you're going from your initial position to your final position. And in this problem here, the displacement vector delta r is just that vector which I've just drawn in. And mg, as we said, points vertically down. So when we go to calculate the scalar product of mg and delta r, what do we get? Well, the way the scalar product works here, we're going to get the magnitude of this vector, which is just mg, times the component of this vector that lies parallel to mg. And you can see from the drawing here that the component of delta r that lies along the line of mg is just going to be this vertical distance here, which we're calling h. So the work done by gravity in this case is just mgh, and you should convince yourself that the work done is a positive quantity, as we've calculated, that gravity is acting in this case so as to increase the speed of the mass, so it's clearly doing positive work. Okay, so we've calculated the work done by gravity, the first term on the left here. Now we need to calculate the work done by the string as the mass moves from its initial position to its final position. Well, in this case, the work, the force is not constant. The work done by the string, the direction of the force is changing and the magnitude of the force is changing. So you might think it's pretty complicated, but in fact, it's quite simple because as the mass moves along this circular arc, the tension force is always perpendicular to the displacement. So you can break the motion up into little steps, and each step of the way, the force of the string points this way and the displacement points tangentially along the arc of the circle. So you break this up into little steps, and along each little step, the string is doing zero work. And if you add up a bunch of zeros, what do you get? You get zero. So the string does no work here, only gravity does work. So the work kinetic energy theorem then tells us that the net work done by all the forces that act on the system is simply mgh. And according to the work kinetic energy theorem, that should be equal to the change in kinetic energy, which we've argued is 1/2 mv max squared. And clearly the m's cancel here. And if we solve for Vmax, we find that Vmax is equal to the square root of 2gh. So let's plug in a number to see sort of order of magnitude of what we expect to get, and the kinds of pendulums that you're going to construct at home, where you just hang a simple mass from on a string, you attach it to a table and it dangles. It'll be easy to get values of h on the order of 1/10 of a meter. That's just 10 centimeters. And then you let it go. And what's Vmax going to be? Well, Vmax in that case is going to be equal to the square root. Let's call g equal to 10 just to simplify things. So that'll be the square root of 2 times 10 times 1/10 meters per second, or radical 2 meters per second, about 1.4 meters per second. So those are the sorts of numbers you expect to get for the kinds of pendulums that you're going to test experimentally, and we'll see if our theory works. So that's it for this worked example. Hope to see you again soon. Bye-bye.